Okay, class, let's continue. So, as I mentioned in the previous video, this is a simplified version of the Mason's rule. Now, I'm going to introduce the complete and official version of Mason's rule. Now we'll see what is the simplification and the specificity of this particular function we discussed about. So, Mason's rule. Now, to define Mason's rule, apparently we have two terminologies. One is the direct path, the other is loop. So let's first officially define what are they. Direct path. So direct path apparently is a path originated from the input to the output. Following the signal flow. Meaning the arrows in the block diagram. Okay. So no backtracking. Apparently. And no repetition. So you cannot repeat a path. If you repeat, that's not direct path, meaning you basically will enter a loop somewhere. So no backtracking, no repetition. So that brings us the notion of loop. Loop will be a path that starts and ends at the same signal. Okay. Starts and ends at the same signal. And of course, when we look at the path, identify the path, we also have to follow the signal flow. The arrows. Still no backtracking and no repetition. Otherwise, you can go on the loop again, but that won't be necessary. We only want to go back to the original place. We don't want to have any repetition. So this defines the two. And in some cases, okay, you may have more than two direct paths. Now, in all the cases we have about, we only have one direct path. But in the general case, you may have more than one direct path. So it's possible to have more than one direct path. Right? The simplified version, in all cases, will only have one direct path. That's what makes this special. Second, about the loops. Loops may be what we call it touching or non-touching. Touching and non-touching is very intuitive. Touching means they have shared blocks. Okay. Non-touching means they have no shared blocks. And let's just quickly go up to the example we have. Now you have 3 loops, right? Are they touching or are they non-touching? Right, if we go up to this one. So you have 3 loops basically. If you choose a pair of loops, you have 3 possibilities for 3 pairs. 1, 2, 1, 3, and 2, 3. Let's look at loop 1 and loop 2. Loop 1 here, loop 2 here. Are they touching? Apparently they're touching because they share G3 block. Both of them have G3 involved in loop number 1 and loop number 2. What about 1 and 3? Both loop 1 and loop 3 has G3 and G4. So these two are shared, so they are touching. And finally, 2 and 3. If you look at 2 and 3, are they touching? Yes, they are touching because G2 and G3 are shared by both loop number 2 and loop number 3. So they're all touching. But apparently we can easily give examples where you have non-touching loops, and we'll give some examples after this. In the general form of Mason's formula, we have to distinguish multiple direct paths in touching or non-touching loops. So in general, the Mason's rule said that if you have the structure, then the transfer function from the input to the eventual output is calculated like this. So it's the sum, okay, of all k. K is the index for the direct path of tk, and times special thing called delta k. I'll discuss what this delta k represents. This will be your denominator, your numerator, and denominator is a capital delta or the big triangle. So k means all the direct paths. So we have to define each of these individual terms involved apparently. So tk is the gain of the kth direct path. There can be a number of them. And this will first define the delta, the big delta first, and then we'll use big delta to define this this delta k above. So this big triangle is a relatively long formula. In general, it can involve infinite number of terms. So 1 minus, the first 2 terms are very familiar. 1 minus all the loop gains. This is what we have in the simplified version. 1 direct path divided by 1 minus the total loop gains. But in general, since you have touching or non-touching, they have to be taken into account. So plus summation of the product of all pairs of non-touching loop gains. Non-touching loops. Okay. So you have to find all pairs of loops and then within those pairs find the pairs that are non-touching, and then multiply the gains of the 2 loops involved in this pairs, and just add all the loop gains together. Okay, but this is not the end. This is only, one term. You have, as I said, so many terms involved. You have pairs of non-touching loops. You will have triples of non-touching loop gains. You can have quadruples of them, and so on and so forth. So we'll have minus. So minus plus minus. This will be product of all triples. So we find combination of 3 loops that are non-touching. Calculate the product of all 3 loops gain and add everyone together, and then of course plus, those will be the quadruple ones minus 5 in the combination, and so on and so forth. Now, in the example we have above, we have the first term, we have the second term, we have 1 minus the total loop gain. And since in the example we have above, you have all 3 loops and the loops are all touching, there are no pairs or triples or combinations of loops that are non-touching. This makes this big triangle much simpler. So this applies to what? This applies to one derived path, and then all loops touching. Right? At least we know these two. Of course, there's one additional term we haven't defined. We have this big delta k, and this is something we need to define in order to proceed. Okay. So let's finally define this delta k. This delta k will be the kind of the coefficient that you need to multiply to this tks. And what are they? They are simply the big triangle up there with all terms that are involved in tk dropped. What does that mean? Let's go up and look at it. Now we have one direct path, right? This from, let's look at this one. From R to Y, this is my direct path. And if we look at all the loops, no matter which loop you calculate, this loop always involves some blocks from the direct path, right? So it means if you look at the loop gains, each one of them has G involved or has something in the direct path involved. If they're involved, they will have to be dropped. So if we look at delta, the loop gain calculation here will have this G's involved. This product will have that involved, all the triple products or pairs in this case will have all the G's involved in this particular case. And if that's the case, we have to drop all terms, we have to drop all of them from delta. If we drop all of them from delta, the only term that is left is this number 1. So that's the third special condition. So that's the first two. The first, one direct path, 2, all loops are touching, and 3, all loops I'll do touch the direct path. Okay. If a loop touches the direct path, then it must involve a term that's calculated in that direct path, and in the calculation here it must be dropped. But there might be, if you have more than one direct path, okay, then it's possible that some loops doesn't touch that direct path. In that case, this delta k term doesn't have to be equal to 1. It may equal to something else. Okay. So that makes things much more complicated, but in this example it doesn't show that way. Okay. So this is the complete Mason's rule. When we apply that, it can be very complicated. In the homework that you're going to work on this this week, you have some problems, some questions, and that should be viewed as the same level of difficulty as the problem you will see, for instance, in the exams. Okay, so that's the Mason's rule, and we'll stop this video here. In the next video, we'll discuss a couple of examples illustrating how to use Mason's rule and manipulating the block diagram to calculate transfer function. Okay.